13, which is code converters. And we have two types. We have decoders and encoders. So what's the difference between a decoder and an encoder? Does anybody in here know? Right, so it takes a number in a different form and changes it to binary. So what does a decoder do? Which would be what? To another form. And we looked at several. We looked at the 74138, which is a binary to octal. We looked at the 7442, which is a binary to BCD. Then we looked at a 7447, which is a binary to 7-segment, right? Binary to 7-segment display. So we looked at a 7-segment display, right? And we talked about the 7-segment display. Yeah, and we have two types, if you remember right. We have a common anode and a common cathode. So the 7447 is a common anode driver. So what that means is inside the LED, inside the 7-segment display, all the LEDs are connected together, but the anodes are connected together, right? So what we would have is we have 8 LEDs inside there. They call it a 7-segment display, but they always have a decimal point. And so we got, and normally we don't put the little dashed line. So normally a symbol for an LED is either this with lines going out of it, or it's this with it colored in. So it should be colored in, or the line should go straight through. Those are both common symbols. When we draw the 7-segment LED display, normally they don't put the arrows because they don't have enough room to put them. And you know you're dealing with a 7-segment LED display, right? So it's no use drawing those. So what we got is we got 7 of them. And what do they call it? What do they name the segments? 1, 2, 3, 4, 5. No, but what are the segments' names? The segments have names. Yeah, the segments have names. They're letters, but they're names. So we have a 7-segment display. I'm just going to draw it roughly like this. What do we call this segment right there? Yeah, that's the A segment. That's the name of that segment, right? You understand? And then we just do what? B, C, D, E, F, and then G would be in the net. And then we have one little dot over here, and they named this DP. I wonder what DP stands for. Decimal point, right? And you can buy them with left-hand decimal points. You can buy them with right-hand decimal points. You can buy them with colons, but you can buy them with colons too. And what they do is we have two options up here. We can come up here and connect all the anodes together. And then we'll hook these to what? What will we hook the anodes to make them forward bias them? What are we going to hook them to? Are we going to hook them to voltage, or are we going to hook them to common? Huh? Yeah, we're going to hook them to the voltage. Now, normally in TTL, the predominant power supply in TTL is plus 5 volts, but that don't mean, because we usually use VCC. So in digital, there's some terms. In solid state, VCC can be any voltage. In digital, it's not. It's 5 volts, and it's usually plus or minus 5%. And then we have what's VDD. This is plus 12 volts. And then we have a VEE. This is a minus 12 volts. So these, when you see these terms, that's what they mean. In digital, that's what they mean. It's the drain voltage on a FET. On an FET. Yeah. An FET is a type of transistor that's used a lot in digital circuitry. Um, they're used in CMOS, complementary metal oxide semiconductors. Those use FETs, and these are just the names of the voltages. So this would be VEE, which is, so they kind of jump between. VCC is a term we use for the collector voltage on a bipolar transistor. VEE is, I'm sorry, I got that wrong. I'm sorry, VEE is right. And then we got a term called VSS, and this right here is your common. And that's just over time. And these all come from the power supplies on solid state devices. And these are terms we use for power. So normally if you see two letters that repeat themselves, these are talking about power supplies. Now, in solid state, you'll learn VCC is the power supply, VDD is the drain power supply, VEE is the emitter power supply, and VSS is the source power supply. But in digital, we just don't learn that. What we learn in digital is these letters represent these voltage levels. In solid state, these voltage levels can be anything. VEE could be common. VCC could be common. So, but in digital, these voltages have a meaning or a level that we deal with. So that help you? So we'd come up here and connect this to 5. What would happen if I come over and connect this directly to common? Didn't we do that in class the other day? Huh? What would happen? Or did we do that in solid state? Didn't we burn one of these things up? Huh? Yeah. LEDs, when they're full diodes, once you exceed their barrier voltage, them suckers act like closed switches. So this would be like me coming over here and hooking up this circuit like this and connecting this side to common and come up here and connect it to plus 5 volts. What happens when I close the switch? What do we have? We call this a special, we have a name for what happens. We call it a short circuit. This burns stuff up, this catches things on fire. So we always protect our LEDs and our diodes with a resistor. Okay, y'all understand that? So we always have a resistor. The other day I talked about we could put a resistor up here, but what's the problem with that? Yeah, what happens is every time you turn on one, it supports the current for another diode, and the resistor drops more voltage and the lights get dimmer. So the preferred way is to do what? Yeah, to put a resistor in here. And then we'll hook up this to and then we would hook this up to our 7-segment decoder, which we're going to use a 7447, which is a common anode driver. So this is what we got. We got a common anode 7-segment display. It's usually a 7-segment. Well, it depends. Sometimes they use liquid crystal, but sometimes they use light emitting diodes, and they're just behind a red screen, so it looks the same. Yeah, you see that a lot. A lot of cash registers use LEDs, still use LEDs. We're going to a 7-segment display, which is still basically the same, except they're not common anode and common cathode. They work on the principle of liquid crystal. Liquid crystal, and I forgot what the crystal is. I should know that, but the crystal they use, if you put AC on them, it causes the crystal to go in a helix or a curve. And what happens when you shoot a light in the back, so these guys are backlight, what we do is we shoot it through a polarized lens, and then the lens on the top, I'll have to draw it, 3-dimensional. The lens on the top is polarized opposite. So we have two lenses, and then so this one might be polarized this way, and this one up here is polarized this way. And what happens when you put AC on the crystal, on the on the liquid crystal, what happens is they line themselves up. So what happens if you shoot light in here, the light comes through and it's blocked by the other lens, right? Because they're polarized. When we put AC on it, it causes and you can't draw it. It causes the liquid crystal to form in a helix. It forms in a curve. And then what happens is when the light moves through, it follows the helix and comes out and it's viewed on the other side. So that's what you're looking at. Have you ever looked at these guys with this? Did we do that in this class? Huh? We did that in this class. Well, that's what you're looking, and what we do is we put a colored lens up here. And so we turn it on and we put AC on it and it straightens up and it blocks it and nothing's seen. Then we take the AC off and it curves and the light follows that helix and then comes out the top one and goes through a red, green, or blue lens. And that's the way that's the way liquid crystal works, which is real neat. What's nice about liquid crystal the big advantage of liquid crystal over LEDs, it's a little harder to deal with. For one thing, we got to have AC, and they're powered off DC, so we got to have an oscillator in there to create AC. Another thing, one thing nice about these guys is they basically use no current at all. Well, it's an unmeasurable current. So these guys last forever. I mean, so you can run these liquid crystal displays off of. So this guy right here, what does it run off of? That's solar. Yeah, that's all it runs off of. So it's taking the light off of these fluorescent lights. Put this. So that's liquid crystal right there. But it's still 7 segments. You understand? It's still 7 segment, but it's not light emitting diodes. It's liquid crystal. It just takes a little harder to. And liquid crystals, you got to be careful with them. You don't want to get them real hot because they'll turn black on you. Ever had that happen to you? So anything above the VF of the diode would be considered to be a short circuit. So that's why we have to put those resistors down there to protect it. Oops. And then we would hook our 7 segment, then we'd hook our driver chip up down here. So that's what the 7447 does, is we put a binary code into that sucker and it figures out what segments to turn on. It decodes it to a 7 segment display. So when we look at our lab, you're going to be required to do some stuff. I've got the circuit wired up, but y'all still got to do some stuff in here. So what do you got to do here? Yeah, you got to do the pinouts of these ICs, right? And we're doing a 74174, which is an encoder, and a 7447, which is a decoder. Are you okay there? Okay, where are you going to get that information at? Okay, then on page 96, we've got a 7-segment display. It's a common anode. They're using one resistor, but I'm using a resistor pack. And this is not the pinout for the common. This is not the pinout of the guy that we're using. Where do we need to look for the pinout for the chip that we're using? On the data sheet. Where's that going to be at? It's going to be up on Blackboard. So all them pins on there, those 1, 2, 3, 4, 5, 6, that is not the 7-segment display that we're using. So you need to mark those out and then go on the Blackboard. And then put the pin out on there. So you need to develop the pinout for the 7447, which is the one we're working on now, and then later the 74147. So the 7-segment display that we're using should be up here somewhere. Oh, I think I'm in the wrong class. Yeah. So that's the 7-segment display we're using. It's got 2 power pins. You don't have to hook both of them. What they do is just to make it more convenient when you put these things on a circuit board on where you put the power pins in. The one we got has the same pin spacing as a 14 pin dip. So what that means is that we can put this thing inside a socket, right? Where's it at? Huh? No, this is the 7447. I'm looking for the pinout of the 7-segment display. Sorry. Yeah, so this is the Common Nano 7-segment display that we have. Yeah. And we're using, so you can buy this in different versions. So the LSD 221 is a common cathode. The LSD 222 is a common anode. So this is the one that we've got. We got 2 power pins we can use. We can use what? Pin 3 or pin 14. And here's so pin 1 would be for what segment? For the A segment, right? You understand that? Then pin 13 would be for the B segment. So are you okay? Huh? What'd you say, Barry? No, it's the 7447. 74147 is the encoder. Just one digit makes a lot of difference. We've got the 7447, which is a 7-segment common anode. Huh? Yeah, but we're doing the 7447 first. So I wired this circuit up completely. So instead of using the trainer, I wired it up completely. So here's our 7-segment display up here, our common anode. Here's our resistor pack. We talked about resistor packs, right? So instead of me having to use individual resistors, I can use a pack. This is a 74. This is not a SIP. This is a dip. A SIP would only have one. The pins would only come out one side, and those are used predominantly as pull up or pull down resistors. When we have to use an actual resistor, which we have to do here, because these are not pull up and these are not pull down resistors, these are strictly resistors, then we would use the dip. This is a 7447. Then I got another 1K. This is a 1K resistor pack. Here's my switches that we're going to be using. Yeah, so I'm not using the trainer. I'm actually wiring the circuit up. I mean, just like it is on the diagram. Are we okay? Y'all understand? Yes or no? Huh? So I'm not using the trainer. I'm actually using these switches. So what we have is we have pull-up resistors, and then my switches provide grounds, right? So here's the grounds over here on all my switches. Here's power. So this would have been better if I used a SIP, because look what I had to do. I had to connect power to all the resistors. If it was a SIP, and then I could have connected the power to a single pin. It would have been convenient, but we don't have any of them around here. So, and then over here, these are providing our inputs. And what inputs do we need? Well, we need, something's missing. I'm missing some wires. Did somebody rip me off? Let's go back to the schematic. So here's my ABCD inputs right here. And we're using switch 8, 7, 6, and 5. Then I'm supposed to hook up my lamp test. What's the lamp test on the 7447? 7447, right? Okay, so I'm going to bring it over to a pull-up resistor, and then I'm going to run a jumper over to 3. 1, 2, 3. So here I'm using here I'm using switch 1, and then I need my Ripple blanking input, RBI. What pin is that? Yeah, can't be 5. I already got something hooked up there. What is A? Okay. What's B? What's C? Is that what? What? No, it means it's low active. It's not a regular A. So the output, we're using a common anode display, right? So we turn them on with lows. We got 2 ways we can indicate lows. We can indicate it with a line above it, right? You understand, low active, or we can even indicate it with a dot. If you look at the actual diagram, the schematic that we're wiring, so the pin out shows it as not A, or low active A, right? But if you look at the actual schematic, how do they indicate the low active outputs? So I'm looking at page 97. So how do they indicate the low active output there? With a bubble. Okay. So the pin out shows the bar over it. The schematic shows the bubbles. Which one's right? Both of them's right. We can use both of them. That's 2 ways we use. We do that on all our, even on our Boolean algebra. When I indicate a low active signal, I put a bar on it, right? You understand? So the pin out shows a bar above the ABCD, and then the schematic shows a bubble. They're both right. Y'all understand that? Okay. So the 7447 outputs a low. So we got some stuff to do here. Undoubtedly, I've got something hooked up wrong, or something's been disconnected. So the A input to the 7447 is which pin? There's no such thing as A1, A2. It's the letter A. Well, let's rephrase that. Different data sheets talk about weighted binary in using different names. So let's see what this guy uses. So before I say that, so we have 2 ways we can do that. Well, we can do it with ABCD, which is what I had in my head, and I might change this out because that's the way I like it. This is DM. This is National Semiconductor. So this is the way National Semiconductor. So here's our inputs. This A. So this is the least significant input right here. Okay. So this would be A. This would be B. I'm sorry, this would be A, this would be B, this would be C, and this would be D. Yeah. So A0 is the least significant. Then it would go what? This would be 2 to the 0. This would be 2 to the first, 2 to the second, 2 to the third. Okay? And I've got those hooked up right. So y'all were saying 13, but 13, this is not the input. This is a what? It's an output. So I was asking where the ABCD inputs were. National calls them what? A0, A1, A2, and 3. I look at my schematic, which is what I'm looking at. They call them what? On page 97. What do they call it? Huh? Can I help you? No, the actual this is a special training center. The actual automotive program is up on the hill in what we call D building. And this is not automotive. This is mechatronics. So I don't know what. Jason, what's Jason Alderman? He's one of the instructors. I think Larry retired, so I don't know who took his place. Tom Behrman's over the program. His office is in here. He's over the whole automotive program. I'm sorry, his office is that way, but when I just look, it's locked. So I guess I don't know. I'm not responsible for automotive. Yeah, yeah. That's okay. You're no problem. I wish I could help you, but that's not my program. So yeah. So on the schematic on page 97, they call the inputs what? A, B, C, D. So what would A be on this guy? It would be A0, right? What would B be? A1. What would C be? A2. And what would D be? A3. Here's my outputs. What would this A be with the bar? This is an output. This goes to A segment. So when you come up here and assign your pins, so you're going to have to assign pins. It's got 1, 2, 3, 8, 7. Is that the way ours is laid out? No, it's not. We don't get this one. We hadn't been able to find that one. So how's ours laid out right here? So 1 is A, 13. So you can still use these, right? 1 is A, 13. Does it have a 10 on there? 10 is what? C. Let's look. Wait, that's not going to do us any good. Hold on a second. It's going to work. But notice it's laid out just like a 14-pin deal, but it's got some pins missing. It goes 1, 2, 3. Then it goes what? Then it goes 5, 7. If we looked at the 7-segment display, what we'd see is I'm not going to pull it out because it's not the same one. What we would see is we'd see the spacing and everything's exactly the same thing as a 14-pin dip, as far as the spacing between the pins and then the length between the pins. So what y'all got to do, you got to draw the connection between the what? 7-segment display and the decoder. Are you okay? You know what y'all need to do there? Yes or no? Huh? So we're using, on my switches, they're not labeled 7 through 1. Mine's labeled 1 through 8. So I have 8 going to segment A. Let me make sure. So I've got 8 going to A. I've got 7 going to B. I've got 6 going to C, and I have 5 going to. So mine's a little different. Notice the switches on the left on your diagram. Let me bring this up instead of me talking. That way I can just show y'all what I'm talking about. Probably gonna tell me it's open in my office. Yeah, I guess. Yeah. Was that the A0? Okay. Oops, that's the wrong one. This is it. So the National Semiconductor, they labeled the A input, not the A output. They labeled it A0, which is down here on what pin? Pin 7. The B input, they labeled it A1, which is up on what pin? 1. The C input, they labeled it A2, which is where? 2. The D input, they labeled it A3, which is on what? Pin 6. Understand now, Jobert? So A0 is A, not A1. That means right now I have this hooked up, and y'all was calling out those 13s and stuff. That's why I was very confused. But I don't have lamp test wired up. We're supposed to wire a lamp test wired up. Now on mine also, so there's a little different because of the size of the switch I'm using. I'm using a 16 pin. I'm using an 8 switch. I'm using a 8 dip switch. By the way, we call these dip switches. And why are they called dip switches? Because they have the same spacing as a 14-pin dip. So we call these dip switches. And notice it's got 2 positions. It's got on and off. And by the way, you don't want to switch these things with a pencil because graphite is conductive and it'll get down inside the switch and cause problems. So you can say this has been switched with an ink pen quite often. Ink's fine, okay, but not a pencil. No, so don't do that. It's normal tendency people have to do that if they've got it in their hand. Even a mechanical pencil, if you put the lead in there, when it snaps, that graphite is going to spill out into a little bit of graphite will spill out into the switch. So what I don't have hooked up for some reason is I don't have lamp test. So what's lamp test? Okay, now I'm going to use switch 1 for lamp test. 1, 2, 3. Okay. Everybody okay? Which one are they using on your schematic? I can use that one. They're using switch 3, so let me use switch 3. That way we'll be on par. Okay. And then I'm going to hook up, sorry. And then ripple blanking in, I'm going to use switch 2. And that's pin what? What's ripple blanking in? It can't be 2. 2 is, I'm already using pin 2. What's ripple blanking in? RBI. I'm going to look at the data sheet. So ripple blanking in is pin, ripple blanking in is pin 5. Lamp test is pin 3, pin 5. 1, 2, 3, 4, 5. Okay. 6, pin 3, pin 5. And then ripple blanking out is pin 4, which says it's supposed to hook to 1. Okay, y'all with me so far? We okay. So I hooked these up. I thought I did anyway, but undoubtedly I didn't. Now what I'm having to do is jump them to a pull-up resistor and then go over to. Okay. So it says I'm supposed to open all the logic switches, right? I'm looking at my first, the following circuit demonstrates, so y'all see the circuit, right? Huh, I don't see my camera. Okay. So here's my 7-segment display. Here's my 330 ohm pull resistors. Here's my 7447. Here's my pull-up resistors for my switches. And here's my switches. Here's power because these are pull-up resistors. And then I have this side of the switches connected to common. Okay. And what does it say? Okay, so all the switches are open. Something's not working right. Hold on a second. Okay. And what happened to the display? Why? Well, when I open a switch, what do I get on? So I'm not doing a lamp test, right? Y'all understand that? Why am I not doing a lamp test? By the way, y'all put the pin out on the schematic, right? Y'all supposed to do that, right? It's part of your lab. Why am I not getting a lamp test? So all my switches are open. If I open up the switch the way it's wired, what do I get? Do I get a low or do I get a high? Huh? If I open up the switch, do I get a low or do I get a high? Get a high because the pull-up resistor pulls it up, right? You understand that? So am I doing a lamp test? Yes or no? Why do you know that? Because it's low active and I'm putting a watt on there. High. Am I doing a ripple blanking input? Yes or no? Why? Because it's high and it's low active. Am I doing a ripple blanking a BI input? No, because it's high. So that means I'm putting a watt into this thing. I'm putting all highs, right? So why does my display do that? Well, what I'm going to do is I'm going to go over to my data sheet and I'm going to look what I get when I put all highs in there. Let's see if it shows us on this. There it is right there. So I put 15 into that thing. So what does it give me for 15? Gives me a blank, right? So that's what we're seeing. Everybody understand that? So that's why. That is the code for a 15. So this guy right here, it'll display all 15 combinations. It represents numbers from 0 to 9, which is BTD. If I put a 10 on there, it's going to display this, right? You understand? If I put an 11 on there, it's going to display this, 12, 13, 14, 15. Okay. Okay, so what's the next thing it tells us to do? The next one ain't going to do anything. Let's do it this way. So what I'm going to do is I'm going to put something in. So what do y'all want to put in? Okay, so let's put in a 5. I keep trying to do this, but my camera is not up here on this list. My camera's down here. Okay. So here's A, B, C. I'm going to put in a 5. So I'm going to come over here and put this. And I'm going to come over and put that. Oops. Let me look at that again. Oh, I'm sorry. I'm going to put in a 5. Okay. And what did my display? A 5. Okay. Are we okay? I keep getting confused. So you turn the switch on for a high. You have to turn the switch. I'm sorry. You turn the switch on for a low. Okay. So there's a 5. Now what am I going to do? Well, if I'd have done what the thing said, if I'd have closed the ripple blanking input, it would have done the same thing it does for an F. So what switch is that? RBI. RBI is switch 1. So what did it do? Don't look like it's doing anything, does it? Let me do. Here's lamp test. What do you think lamp test will do? Which is switch 3. Yeah. So here's lamp test. Huh? Because the 7-segment display does not run the 7447 does not run the decimal point. We have to run the decimal point external. So I'd have to come up with some circuit to run the decimal point. Because a lot of times we don't use the decimal point. All we want is a number. So if you look at what the 7447 decodes, it's A, B, C, D, E, F, G, but there's no decimal point. Because how does it know where the decimal point is supposed to be lit? It don't. So that answers your question? So all the segments wrong. So even though I'm doing a 5, so it don't make any difference what I'm doing. So there's a 5. I mean, I could put any number in. So there's a 7, right? And as soon as I do the lamp test, it's going to come up and display. It's going to turn on all the segments, which is pretty good. A lot of times they will look that up, but you know it's available, right? You understand. So if you was having a problem with one of your displays and you wanted to see if your 7-segment display was wrong, if you could ground that pin and all of them come on, then it's not the display, right? You understand that? It's probably not the 7447 either, because it's doing what it's told to do. Okay, so that was which step? That it don't tell us to do that, right? Yeah, switch 3 will be closed. Open switch 5. Switch 3 would be closed. Okay. Then it's asking for close the BIO input. That does nothing because that's an output. The pin they want to do, let's change B to RBI. So they don't ask for the RBI input anywhere, do they? Okay. So step B, let's change that to RBI, and I'll make a correction on that. So let's see what happens when we do. I'm going to take off lamp test. Okay. So there's a 7. So I'm going to come up here and close switch 2, which is RBI, right? And what happens? And we call this, in displays, we call this blanking. No, this is RBI. RBO don't do anything. It's an output. I don't know why they want us to do that. Yeah, so scratch out RBO and put RBI, which is switch 2 on B, right? So we're closing switch 2. So let's make that correction there. Now, a lot of times to save hardware, what they'll do is they'll come up here and they'll put several displays. And you can see this, especially when you take pictures. Or a lot of times when you take video. So what they'll do is they'll have 4 or 5 or 6 7447s, and then they'll come up here and they'll multiplex them. So what they'll do is they'll share the data pins. Which is going to save a lot of hardware, right? You understand that? So this is the way the display on our function generator works. This is a lot of the displays. If you got most of your cable boxes and stuff like that still use LEDs. Use 7-segment LEDs. And that's why it displays those weird characters sometimes on you. And those are multiplex displays. So a lot of times if you snap a picture on it, you'll see only one of them's lit because your camera can catch that. If you take a video of it, depending on the frame rate of your camera, when you take a video, it'll look like it's blinking. Well, what they're doing is they're multiplexing those displays. So what they'll do is they'll place the data on one, and then they'll blank all the rest of them. They'll unblank this guy, they'll blank all the rest of them, and they'll turn off. And then they'll do what? Then it will place the data on the next one, blank the other 3. And then it'll place the data on the data for the next one and blank the other 3. But it's doing this at a rate that your eyes what? Can't see. And it's not too hard. These guys right here are blinking 120 times a second. They're actually, these lights up here are actually turning off 120 times a second. But we see them on all the time. Why? Yeah, the frame rate on most movies is like maybe 60 frames a second. So movies are individual pictures. Y'all know that. They throw them individual pictures up there. But what does your eyes do? It sees it as an image in motion. So each picture they refer to as a frame. So when you're taking pictures, that's what your camera's doing. It's doing what? When you're taking pictures, when you're taking videos, your camera's constantly doing what? Yeah, it's on. It's snapping, and then it displays in rapid succession, and then we do what? We see them as an image in motion. Thomas says it's time we need to take a break. So let's take a break. We'll see. It would surprise me if it does. See if it comes up in a minute and says no video available, then no, I can't update it while I'm using it. So the ripple blanking input is used to multiplex these things, right? You understand that? Lamp test, you see what that's used for. The BI and the RBO, I'm not really sure. It's even confusing in the data sheet. Let's read and see what that is in the data sheet. So where's that at? Right here? No, it's on Blackboard, right? The 74 LS47 decodes the input data in a pattern indicated in the truth table in the segment identification illustration. If the inputs is the decimal 0, a low signal appears on the RBN blanks the display and causes the causes a multi-digit display. For example, by grounding RBI of the highest order decoder and connecting its RB out to the RBI of the next lowest order. So the RBI, and I don't know why they have it hooked up to a switch. The RBO is actually a what? What does the O stand for? Yeah, so it's telling us what we need to do is connect this to the next higher order display, right? You understand that? So we shouldn't even be using switch 1. The only switches that come into play are switch 2 and switch, what's lamp test? 3. Okay. So what's the next thing it tells us? So we've modified B, and I need to make a note of that so I can correct that the next time I give out the lab. That's not the lab. Where's lab at? Oh, it's not PowerPoint. Don't look like I have it open anymore. Okay. So what's the next thing we need to do? Let me bring up the camera, and it's not in my list of. So right now we have it blanked, right? So this is unblanking. Oops, sorry. So there's unblanked, and right now we're displaying a 7. What's the next thing it says? Open switches 1, 2, 3, and closed switches 4, 5, 6, and 7. Now these are I'm using what? 8, 7, 6, 5. So if I open all of them, of course, it's going to blank again, right? But now it's decoding that for a 15. So this is not blanking. Y'all understand the difference. This is actually what it codes for a 15. These switches, except switch 3, what does it display? With switch 3 is what? Lamp test. We've already done that. So let's go through our code. So right now I'm putting a 15 into it, right? Okay. So this is a what? It's not 8. 0, right? So here's switch 8. So now it's what? 1. Here's switch 7. It's what? 2. Here's switch 1. Here's switch 8 and 7. What's that? 3. Here's switch 6. 4. Here's switch 6 and 8. 5. Here's switch 6 and 7. 6. Here's switch 6, 7, and 8. 7. Here's switch 5. 8. Here's switch 5 and 8. 9. Here's switch 5 and 7. Huh? Yeah, but it's a 10. And if we look at the data sheet, yeah, but if we look at the data sheet, I'm putting a 10. That's not the data sheet, Rich. So if I look at the data sheet and I look at the chart, or I can even look at the truth table, but what's nice is it gives us a chart, what it displays right there. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's what now it starts shifting into a code, right? So that's the code for a what? 10. This is the code for a 11. This is the code for a 12. Code for a 13, 14, and then 15. It blanks it, right? Okay. We do have a decoder that decodes all 15 combinations. But you got to imagine how would it do in a, if it did an A, how would a 7-segment display do an A? Yeah. Well, that would be an A would be easy to do. I could come up here and do this, right? No, I'm sorry. What I need to turn off? So it does an uppercase A. Will it do a B? Well, it can't do an uppercase B because it would look like an 8, but it could do a lowercase b. Could be that. Could it do a D? Can't do an uppercase D because it looks like a 0. Could it do an E? Uppercase E, right? And of course it could do an F. So I've seen these things used as a hex decoder before, but you have to learn those patterns, right? You understand? But we have a decoder. It's a 9368. That'll give you all these characters. It'll do hex. So it'll do 0 through 9, then it'll do an A, B, C. I'm sorry, I didn't do C. It will do. I don't remember if it does a lowercase c or if it does an uppercase C. I'd have to deal it back out. So it can do an A, B, C, and D. It's just that the 7447 don't decode it, right? You understand? So I would have to go to a what? Another decoder, like a 9368. A 9368 is a hex decoder, and it would decode these right here. And it's a current driver too. It's not a voltage driver, so you don't have to have pull-up resistors, which is really neat. But I've worked on devices that use a 7447, and after a time, what do you learn? Well, after a time, you learn these codes. So you know what an A is, a B, a C, a D. You learn them after a while, but it takes a little while because the 7447 gives you a code for anything above 9. So it basically does BCD real well, right? You understand? But if you put a 10 on it, it's not going to blow up on you. It'll display something, but it just won't be what we expected to display. That makes sense? Are you okay? So that's a 10. There's a shortcut key you can get to bring up the desktop. What is it? Huh? I'd have to look it up. I usually tab through them. You can on a Windows computer, if you got multiple applications running, you can hit the Alt key and then hit Tab, and you can tab through all the applications that you have running. But there's a shortcut to bring up the desktop. There's a shortcut. It's something. I'd have to look at it. Huh? I think that's right. I think that's right. We'll try it. Most of your shortcut keys are Alt Ds. So that's a, what do we have here? That's a 10. Here's 11. Oops. Didn't change it. Oh, I'm going the wrong way. So there's an 11. So it just swapped size, right? There's a 12. Here's a 13. Here's a 14. And of course, here's a 15. And that's a 7-segment decoder driver. Looks very impressive, don't it? But if I was to come up and do this with transistors, and I could do this with transistors, you would have a sure enough display. I think I told you about they had a post mill machine out at Beach's Machinery. When you go through Fairfield, it's one of the buildings on the right. They do machining for a bunch of companies, and they had a post mill machine that was nothing but transistors. The boards will be about that big and nothing but transistors. Uh, I think I still got the schematic on it somewhere. It crashed on them, and I came in and literally replaced some of the stuff with ICs. It was should have seen it. So I put a mount on it and spun them around and did wire wrap. Y'all seen wire wrap, right? Didn't I show y'all wire wrap? Well, they make sockets where the pins come up, and you can glue them on, and you can wire wrap on the top. And I replaced a whole a comparator circuit with a 7485, and it worked great. Oh, it worked great. So after that, I used to get calls. It got to it was ridiculous. So when the guy started complaining about how much he was paying me, then I decided I didn't need to work there anymore. So we're okay on a 7447. So what is a 7447? It's a decoder or a decoder. And what do we call it? It's a binary to 7 segment. And what does it do? It does a common anode display. A 7448, what do you think that does? It's a decoder, but just think, what do you think a 7448 does? It's a common cathode. So 7447 is a common anode. The 7448 is a common cathode. Common anodes are by far the most common because it's easier to turn things on with a low than it is with a high, right? By the way, this has a the 7447. I would turn it off anyway. It just opens the output, right? You understand that? And then grounds it when it needs to turn it on. So it's acting like a Any questions on that? Okay, so what do we need to wire up next? $74,147. And what's that? Y'all look that up on the data sheet and see what that is. So it's a priority encoder. What's that? So we did the so the way it's wired. So y'all got to do the pin out, right, and finish redrawing, drawing the circuit. Oops, that's not what I want. We'll take that right there. So this is the 7447. It's a 16-pin deal, right? And the 74147 is a 16-pin deal. And this is the circuit I have wired up. What are y'all supposed to do here? Give me the what? The pin out. And you're all supposed to do what? Draw the connections between the 7447 and the display. By the way, up here, you're going to have to name these A, B, C, D, E, F, G. You don't have to put them in order. What you need to do is to put them in an order to hook up to the 7-segment display real easy, right? You understand, without crossing lines all over the place. So what's pin 1 on the 7-segment display? Okay, it's A. So logically, one of these right here should be what? Should be A. In fact, I would probably make it this one and come around, and that way you can come around like this. So you can call this A, you can call this G, you can call them anything you want to as long as you assign the pins right. So what you want to do up here is assign the pins so you don't have a bunch of crossing wires down here when you're trying to hook up your 7-segment display, right? That makes sense? So what I'm using for A, I'm using switch 8. So I've got a My switches, I have 8 switches and not 7 switches. So I'm using 8, 7, 6, and 5. So that's the only thing that's changed. Here I'm using 1, 2, 3, just like wrong. You need to put your pins up here, right? And down here you need to put the name of the pins. So up here they have the name of the pins. Down here they don't, right? Y'all understand? Yes or no? Y'all know what y'all gonna do, right? Yeah, that's where you're gonna label your outputs. Now down here, you're gonna have you're gonna have to hook the circuit. So these resistors don't go nowhere. Where do they go? They go down here to one of these pins, right? Yeah, you need to draw the circuit. You need to draw the connection. Do the best you can. I know it's gonna get kind of bundlesome right in here. They didn't leave us much room. I don't know if I could put that out and do this. I don't think I could. Well, that's what the way you want to do it. What you're trying to do is assign the pins so you have the least crossing lines. That makes sense? Are y'all any more questions? So what do you got to do? You need to put your pin out right here, right? I don't know why they're doing this. Oh no. What they wanted us to do, guys, and the circuit's going to tear down anyway. What they wanted us to do. So let's go back to this step right here. I was wrong. So it says install the 7-segment display and connect the 14 pin to this resistor. The pins will be tested to determine if each pin is determined. We'll do this a lot too. By the way, normally what they do on a 7-segment display is they share the common pin between two sides. So here they say, I think they said it was pin 14 and pin 3. Okay. So normally what you can do if you're trying to figure out what these are, if you got a 7-segment display, is you just use an ohm meter and you find the pins that are connected together. And that'll tell you the power pins. That makes sense? And then what you would do is you'd take a resistor, you'd hook it up to one of your power pins, then you would take the other polarity and you would try to turn an LED on. If none of them turned on, then instead of using 5 volts, I would connect it to what? I would connect it to common, and then I would try to figure out how that thing works. I wish I still had that other one up here to show you how to do that. So normally on a 7-segment display, you can figure that out. So how would you find the power pins? You use your ohm meter. You'd like to put it on one pin, and you'd go down the ones on the other side. If you don't get continuity, then you would move one pin over here and then go down the pins on the other side. You don't have to go down all the pins just on the other side, right? You understand what I'm saying? Go ahead, Barry. What's that? Because we looked it up on the data sheet. I don't have it. I still don't have it up here. I do still have it up here too. So we're using a common anode. Here it is right here. So what's the power? So common anode means we're going to connect power up here. And what's the two ends? Yeah. And 113, and these would be the one with the left-hand decimal point, which basically varies these two numbers right here. These numbers up here. common anode. Then you can buy it as either a right-hand decimal point or you can buy it with a left-hand decimal point. If you bought it with the right-hand decimal point, then you to turn on the decimal point, you use pin 9. If you bought it with a left-hand decimal point, you connect it to pin 6. That makes sense? So when you go up and buy these things, now we'll just look at Jamico, and then we'll look at, dang it, it did a search. And most of the time when you use this first one up here, you usually get an error. I needed to go. So we'll just say 7-segment displays. So when you buy them, so this is the way. Oh, these are decoders. So 7-segment display, common cathode, and what color is this? This is red. Let's look at the catalog pages. Y'all see where the catalog pages are at? By the way, they give away the catalog free, so you can go in here somewhere and order a catalog. And sometimes that's a lot easier to use than trying to figure out how to get through the website. So this is the way you would actually see them right here. So it says, this guy right here, it says this is their number, this is it, and it says it's red, then it says CA. What does that mean? Common anode, 14 pin. This is the VF, so it's going to take about 2 volts to turn this guy on, and it's going to pull 20 milliamps. And that's what we'd use to size the resistor, right? Does that make sense? Gives us the wavelength, which is pretty, the wavelength gives us the color. So anything around 600 nanometers is in the red wavelength. But you can see these things come in quite a few different colors. But they're either going to say what? CA, or they're going to say what? CC, Senor. CC, Senor. And this is the way they look when you look them up in a catalog. That makes sense? What I like about Jamico is that when you go to the actual part, what they provide on everything they've got is what? Data sheets, which is really, really neat. I really like that about Jamico. So most of the time when I want a data sheet, I don't go to the internet and search it, because you get all these different places that want to charge you for them. Your data sheets. Or you got to give them a lot of information before they give them to you free, and then they sell that information. So Jamico, you don't sign up for Jamico or anything. It's just Jamico.com, and they sell a Jamico, www.jamico.com, and they sell a bunch of parts up there. So just a lot of these data sheets actually came from up there. So any more, y'all know what y'all going to do on that lab? Y'all can do that. So let's hook up. I need to get another trainer. What have I got on this trainer? Oh, I've got the. We'll use this trainer. So here, to save time, what we'll do is we'll use the data switches. And of course, I did that for one reason, to show you how more convenient it is to use data switches instead of wiring up those switches. So let me get the trainer up here and so I can get the camera. I might have to set the camera. I'm going to set the camera in the lid, and then we'll turn the camera on. So about 7447, I usually put mine with pin 1 painting to the left, so that way, uh, then I run power over here, and I usually do it so you don't have to cross your wires coming over to this side over there. So this is the 74147. So y'all tell me how to hook it up. So what's the power pin? Ground is 8, which is pretty common, but when we started in flip-flops, we know that that's not always true, right? Okay, so what else do we need? Got to use a lot of switches here, right? We got to use all 8 of our switches, it looks like. Looks like we need an extra switch too. So let me get my. Oh, here it is. No, what we use is we'll use one of the D-mount switches. That'll be easy. Okay, so what do we need to do? We need to assign switches. How you want to assign them? I'm listening. Good gracious, Rich. I use this one in my cable splicing course. So looks like we probably input 1. We'll probably hook that up to switch 0, right? So what's input 1? What's that? Is that on the 74147? What's input 1, I1? Let's look at the data sheet first and see what data sheet we got, and see if they nomenclature it the same way that dang it, I lost Blackboard. So y'all have the data sheet on the 74147 in there? Huh? And we'll see how this data sheet nomenclatures the pins relative to our lab. It's got the 74147 on there. You don't get to use your book on a test. So what do you think? So here's the 7447. Looks like our inputs on here are just labeled 1, 2, 3, 4, 5, 6, 7. Looks like it's pretty simple. Then it looks like the outputs are labeled A, B, C, and D, right? So that looks pretty easy. Huh? I'm listening. Yeah, the outputs are going to be A, B, C, D. So this, I like this one. The book's not really, I mean, the lab is not really good. So here's our inputs. So here's input 1, 2, 3, 4, 5, 6, 7, 8. Here's our outputs. A, B, where's 9 at? Now, 9's over here on 10. I don't know why they did that. Here's our inputs. I mean, here's our outputs, A, B, C, and D. So the outputs on your schematic, they're calling it A0, A1, A2, and A3. Right. Because here we're going from a code to binary. So we'll put our code in over here. So we can put in a decimal over here, right? 0 through 9. I mean, 1 through 9. 1, 2, 3, 4, 5. We need 9 switches. So I'll use the knot over here. So I'll have to pull it down. So what I'm trying to do is trying to hook up the number 1 input. And we'll hook that up to switch 0 because we got to use all of them, right? Okay, so what's the number 1? What pin is the number 1 input? Huh? Okay, so 9, 10, 11. Now notice when I hook up my chips, I put the wires as far as away as the chip I can. I try to leave my chip open up so if I got to troubleshoot it, I can get my logic probe into the chip and I don't have to stick it through a bunch of wires, right? That makes sense. And also later on, if we have time, golly, if we hook up a logic analyzer to this thing, then normally what we use is we use these devices called chip clips. So if I'm going to hook a scope up of this thing, then normally what we would have to do is we'd have to pull the tip off the scope, which opens up a ground, and we try to get it into there. So normally what we do is we buy these things right here. These are called chip clips. And then we can just come over here and clip them onto the chip like that. And now I've got these nice big old posts up here that I can sure enough hook things up to, right? So these are called chip clips. They're not very expensive. Y'all see that? Ain't that neat? And now what can I do? Now if I've got a logic analyzer, I can come up here and hook up all these pins without trying to get into the chip itself. And if I'm using a scope, what we do on the scope is we can come in here. Oh, on the scope, you don't try to push it in like that. What you do is you come in here on the side, put it vertical, and then you roll it over. Now you can latch the scope onto that thing and just leave it there, which is pretty neat. So these are chip clips. You can buy these all shapes, just about all the chips you got out there, all the dips. You can buy chip clips for dips. Huh? Is that one broke? That is. Because 105. There it is right there. So you can buy these 64. Chip clips. Well, if I bring my wires all the way in, I won't be able to get my chip clips on there, right? So if you do a lot of digital troubleshooting, these things are really, really neat. Okay, so I'm going to hook up my next one. What did I do with my long wires? So input 1, input 2. Where am I going to hit input 2 up to? I'm going to switch 1, 12, 9, 10, 11. What's the other one hooked up to? 9, 10, 11. 9, 10, 11, 12. Okay. Input 3. What's it hooked up to? Input 4. What's it hooked up to? That's where we're at, right? Input 5. What pin? 7. They swap sides on us. Everybody agree with that? Y'all telling me how to hook it up. I'm just hooking up. Input 3. So here's input 1. Here's input 2. Here's input 3. So we're working on input 4. What is input 4? Okay. Input 5. Input 6. Input 7. Input 8. Input 9. What's hooked up to 9? Anything? We'll double check this. So it looks like I might have hooked up some things wrong. By the way, when you strip these wires, you don't want to strip them this long. What you'd like to do in digital is you like when you insert these things in there that your insulation is almost right into the board, right? Because if you get a bunch of bare wires sticking up there and you're hooking up all this circuit, it's going to be impossible to keep them from shorting out. So undoubtedly we use this thing here for something else. So this is 9. Where does it go to? What? No, input 9 can't go to A. Input 9 goes to what? 10. And I've got a wire that's popped off somewhere. So 1 goes to where? Okay. All right, so input 1 I have going to 10. Okay, so input 1 I have going to 9, 10, 11. Input 2 I have going to 12. Input 3 I have going to 13. Input 4 I've got going to 1. Input 5 I've got going to 2. Input 6 I've got going to 3. Input 7 I have going to 5. 4, sorry. And then input 9 I have going to 10. Okay? Did I leave that one off? Okay, input 8 I got going to 5. Okay, so now we need to hook up our outputs. So what is the A output hooked up to? Okay, we're going to hook that up to the 0, so that way they'll be in order. Okay, I'm going to have to strip another wire. What's the B? Okay, I'm going to hook that up to, yeah. Yeah, A0 would be A. A1 would be B. Yeah. So what's our gauge wire? We're using 22 gauge wire. So B is what pin again? Okay. And we'll look at it up to LED 1. C is pin. And I'll hook that up to 2. LED 2. And the D is pin. I got something going to 14. Oh, let's see what I've done. And 15 is not connected, right? Okay. So I think we got it. Nothing's going to burn up anyway. So here's my switches. We're using 1, 2, 3, 4, 5, 6, 7, 8. Or 0 is 1. 1 is 2, right? You understand that? And then I had to use this switch over here for my other one, for my last one, which is one of my pulse switches, one of the debounce switches. So this is 9 over here. I have it hooked up to the 0. So that means when it's up, I get a 0. So I'll have to pull it down to get a 1. All right, we ready? So what do I need to do? Oh my goodness. I'll take a break. Y'all see what we got to do, right? Y'all understand what we're supposed to do here? So what is the output of the 74147 supposed to feed? I'm on page 98. Are y'all looking at schematics, right, with me? What's the output of the 74147 supposed to feed? It's supposed to feed a bunch of inverters because the 74, why do we have the inverters? Why do we need to switch it over? So the 7447, so here I come in, I put all highs, which should be, I'm putting all highs in, right? Okay, so what's all highs? Well, it's got low active inputs, so what would it see all highs in? It's going to see it as a 0. Y'all understand? But what does it output for a 0? It outputs all highs because the outputs are what? They're high active. So here's a 1. So here's 9. If 9 goes low, then A goes low and D goes low, and C and D are high. So is that a 9? No, it's a 6. But remember, it's a low active output, so they're true when they're low. So but my 7447 has high active inputs. So when this thing here, y'all understand what I'm saying? Yes or no? Okay. So the 148 has low active inputs and low active outputs. So it's got inputs labeled 0 because this is working on a like this would be fed in from like a 74138. A 7138 has a low active output. So when you bring in a 3 on the 74138, output 3 would go low. So on this one, if I want it to do a 3, if I want this thing to see a 3, then I'm going to bring input 3. I'm going to bring it what? I'm going to bring it low. And this thing sees that as a 3, not as a decimal 3, right? Or an octal 3. Y'all understand that? Now, if I was to convert this to binary, this would be a 3. But this thing has low active outputs. So that means this guy's going to output this for a 3. Yeah, because it's the opposite. It's a low active output. They're true when they're low. This is a high active output. This would be a low active output. Now, the problem is my 7447 has high active inputs. So when we put a 3 in there, this is what my 7447 wants to see. This is what my 74147 outputs for a 3. So what do I have to do before I feed it into the 74147? I have to invert it. So that's what all those inverters are for. So when I look at the truth table for a 74147, this is a 7. So how do I tell it a 7? Well, I put a watt in there. I put 7 low. But what's it going to do? It's going to put a high out the D, a low, low, low on the ABC, which we would see as an 8, but this guy determines it's a 7 because it's got a low active output. But if I fed this into the 7474, it would display an 8, right? You understand? So what do we have to do? Why? So it tells us to put watt between the outputs of the 7447, the input to the 7470, inverters. So it's going to take me a second to wire that up. So y'all give me the pins, and I'll write them down here, and y'all can take a break. So we're going to use a 7404, right? That's our inverter. And they're pretty straightforward. We'll input on 1, output on 2, input on 3, output on 4, input on 4, output on 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Input on 1, output on 2. Input on 3, output on 4. Input on 5, output on 6. Right? And then we'll input on 9 and output on 8. Okay, so that's what we use on the 7404. So what's my A input on the 7447? And what's my input on the 7447? A input, I'm sorry, what's the A input on the 7447? Y'all got the pin out, right? What's that? 9?
No, A is 7.
A is 7. B is what? 1. C is 2. And D is 6. Okay. This will be pretty easy. All I'm going to do is move the wires over. So y'all go ahead and take a 10-minute break, and I'll hook up our 7-segment decoder. But I got to get a 7404. I'll have this wired. let me know. So we're inputting all highs in 74,147. It sees all highs on its inputs. It interprets that as a 0, right? You understand? So it outputs a 0, but it outputs all highs. And what do? We invert it with our 7404, and then run that into my decoder, and it displays a what? A 0. I'm going to put a 1 in it. So what should it display when I click a 1? Should display a 1. Now notice, I'm going to come up here and flip these switches. So I'm going to flip this one. Oops. Sorry. I'm going to flip this one. Now why? I still have the 1 on because it's a priority encoder too. So the 8 has a higher priority than the what? Than the 1. Y'all understand that? I left the 1 up there. I mean, see that? Okay, here comes switch 2. So what should it do when I put input 2, when I bring it low? It should display a what? I'm having problems with my 2 switch. It's going to display a what? A 2. Input 3 should display a what? A 3. Input 4 should display a what? 4. But if I bring input 1, it doesn't do anything because input 4 has a higher priority than input what? Than 1. And that's why it's called a priority encoder too. Okay. Priority. So the 4 has a higher priority than the 1. Right? You understand? It has a higher priority than the 2. It has a higher priority than 3. But it don't have a higher priority than the 5. Yeah, that's why it's called a priority encoder, right? Okay, so here comes a, what do we got? A 4. Here's a 5. I'm leaving the 4 selected. It don't make any difference because the 5 has a higher priority, right? You understand that? Yeah, the highest number has the highest priority. So we could use this in a situation where I'm assigning priorities to different inputs. Yeah, and then each number that's coming in would give me a high priority. We have there's something on computers called interrupts. Have y'all ever heard of interrupts? So what we can do when we output I/O devices, we can do what we call a scan, where that would be like me coming to everybody in the class and I say something. I say, Babana, do you have a question? Jobert, do you have a question? Whether you got a question or not, I'd have to go out and scan all these devices. So right now, I would have to scan that keyboard, but what am I doing with my keyboard? Nothing. So what they did is they came up with a method called interrupts. So what happens is this computer never scans that keyboard, but when I hit a key, it generates an interrupt, and the processor will stop what it's doing and go to a certain place, which is defined in something called a PIC, which is a priority interrupt controller. So we can see the interrupts if we go to, this is Windows 7. So I'm going to go to my computer, and I'm going to go to properties, and then I'm going to go to advanced settings. I'm going to go to device. No, I'm not. I don't want to do that. I'm going to go to programs. I hadn't found it on, and I'm going to go to accessories, and then I'm going to go to system tools, and then I'm going to go to system information. And one of the things we got I/O, and right here it's got what? IRQs, interrupts. So these are the interrupts assignments for this computer. So the keyboard is, I can't remember, I used to know those. So the keyboard is interrupt 1. And on this one, The way this pick is set up is that the lowest number has the highest priority. So interrupt 0 has a higher priority than the keyboard, which has a higher priority than uh, the real-time clock, which has a higher priority than the pointing device, which has a higher priority than the numeric keyboard. So this one, the way this pick is set up, is a priority encoder. And what it does is we have one interrupt pin on the processor, and then all the interrupts come into the priority encoder. And the priority encoder sets the priority. Does that make sense? So that's a situation where we would look at a priority encoder. So look at everything that generates an interrupt. So this computer never scans the keyboard unless you do what? Yeah, and this would be like you raising your hand. So that's the way most classrooms go, or you speak out in my class, but you interrupt me, and I'll come up, and sometimes I finish what I'm doing. So it depends on what we do. Most of the time, what it'll do is it'll finish the current instruction before it honors the interrupt. So here's the RQs. Got a ton of them now. We originally started off with 8. The original pick could only handle 8. And then we moved to 16, and now look at all the interrupts. Look at everything that generates an interrupt. So it's pretty interesting, right? A lot of interrupts. A lot of interrupts, yeah. So that's where a priority encoder would come into play. That's one example. I don't know what I'm looking for. Oh, I'm going back to my camera. I keep trying to get to my... Oh, there it is. My computer hadn't turned off once, has it? So there's 5. Here's 6, which is switch 5, because we start with 0. So it's going to display a what? A 6. Here's 7. Here's switch 6, which is 7. It displays a 7. Here's switch 7, which is input 8. It's going to do what? Display an 8. And here's 9 over here on our... And that's a encoder, right? So what does a decoder do? A decoder takes binary and converts it to certain outputs. An encoder takes outputs and converts it back to what? Binary. And this is a 74147, but we're taking it, low active outputs, inverting it to get high active outputs, so we can fit it to our 7447, which needs high active inputs. And 7447 is a decoder, right? It's a binary to what? 7-segment decoder. And there's decoders. Now, we got a lot of other decoders. We got 74154s, which are 4 to 16 decoders. We got 74138s, which is 3 to 8 decoders. Are you okay? So that's that lab. Y'all got any questions on that? So how would y'all like to wire that up? How long would it take y'all to wire that up? Yeah. So it looks impressive, but you got to understand there's a lot of circuitry inside these integrated circuits, right? You understand? So they take a lot of wires. And it looks impressive. I'm sorry about all this spaghetti up here, but I had to use long wires to get over there. And those long wires I have cut are a certain length. Okay, so what's lab 14? Oh, it's up here. Huh? Okay, what's that? We're not using the 7445, but okay. Oh, really? Which is a latch. Well, so so that's a screw up. So what can I do? Well, let's see. We got this thing called the internet. Yeah, I'm glad you let me know, but I mean, just trying to get the data sheet. So the best place I would go instead of trying to search for it, I would just go to what? Yeah, I just go to Jamico and what? Which one am I missing? Of course, I should have looked. It's probably in the folder. I just uploaded the wrong one. Up here, I'm gonna type in 74 LS 45. Come up here and hit that. Oh my goodness, guess what? Jamico don't sell the 74 LS 45. So let's go to docs. Let me go to ETC. Let me go to digital. Let me go to handouts. Let me go to data sheets. So that's a BCD to decimal decoder driver. So this is what happens most of the time when you come up and go to these data sheets. They want to get information. Oh, there it is. So I'll go ahead and download this. This is not an LS, but y'all understand what's the LS? Well, all the LS is just the speed and power characteristics. If you're looking for the pinout and what the thing does and truth tables and all that kind of stuff, then you'll do that. So I'm going to go ahead and save this, and I'll upload it. It'll take me a little while to get it uploaded to Blackboard. But that looks like a good one. So handouts, data sheets. That looks okay. That title looks okay. So I'll put it. I'll get it up there. Yeah, these PDFs are really easy to download. I mean, normally you get a save. Windows 10 or Edge, you have to come up here to the top, and you'll get a black menu that'll pop down where you get the option to save a PDF file. Not once you get used to it. Okay, so everybody got a 14? No, because they're still all up here. So what does Lab 14 deal with? Multiplexers and demultiplexers. What is multiplexing? So what is multiplexing? What is multiplexing? So have y'all ran into multiplexing lately? You're using it right now. If you're on those computers, you're using multiplexing. If you're using the internet, you're using multiplexing. If you use your cell phone, you're using multiplexing. If you use USB, you're using multiplexing. If you listen to a radio station on your car radio, you're using multiplexing. If you watch TV, you're using multiplexing. So what is multiplexing? It's when we allow, when multiple media, more than one media, I'm sorry, one and more signals share the same media. What is media? Well, that is one media. But what is media? Media is what information flows through. Okay, y'all understand that? So multiplexing is when we let multiple information share the same media. How much information is flowing through this air right now? Yeah, that's about the best thing you say is a lot. All your cell phones, all the cell phones move through the air. These computers are using the air. This is a wireless network. All these computers are using the air. Your cell phone's using the air. All your broadcast radio stations that you pick up on your car is using the air, right? You understand? Some of the TV stations up in Birmingham that still broadcast through the air, channel channel 6 or Fox. We don't call them channel 6 anymore because usually they're spread out where the cable company wants to put them. So multiplexing is, and we have two types of multiplexing. What's the two types of multiplexing? So guys, sometimes I feel like I'm up here talking to myself. We have two types of multiplexing. So Ethernet uses one type, the internet uses another type. So undoubtedly, we're not doing very much studying in this class. So if I gave a test on this right now, it appears that all y'all would probably fail it. And we've lectured on it twice. It was on the recorded lecture, and then I literally came back and re-lectured on that because it was obvious that y'all have problems with online stuff. So we have two types. In network, we call them baseband and broadband. In digital, we call them time domain multiplexing and frequency domain multiplexing. So what is time domain multiplexing? So on this network right now, how many computers can be on this network at any one time? One. That's time domain. But when they're on the network, they get the full bandwidth of the network. Yeah, and we use what we call carrier. We call it carrier access. We call it carrier sense multiple access collision detection. So this works like the old party lines where everybody had the same. We had a lot of people have the same phone number, and before you dial, what was the first thing you did? You picked up and you listened. If somebody was on the phone, you just hang back up. So that's the way Ethernet works. It comes up here. You want on the network, what does it do? It listens to the network. If nobody's on there, it transmits a packet. Don't transmit all your data, it transmits a packet. Usually 4,096 bytes. And then what does it do? Then it comes off. And then it checks the network again. If nobody's on there, it'll transmit another packet. Then it comes off. If nobody's on there, it'll come back on there again, right? You understand? If somebody's on there, they're sitting there waiting, listening to the line. As soon as this guy comes on, what happens? Another guy grabs it. Right? But he gets the full bandwidth. Right? He or she gets the full bandwidth. Comes off after one packet. Everybody's listening to the line. As soon as they see it, somebody grabs it. Sometimes we have collisions. If they have a collision, both the computers come off the line. They have a random number generator in there, and they come back on a random number of times. So odds are they're not going to collide unless the network is very, very, very busy. So if you come in here at like 8 o'clock in the morning and try to get on this network, 8 o'clock is usually the worst time trying to get on a time domain on a baseband network. And why is that? Everybody's coming into work checking their email. So that's the worst time. What's the best time? About 2, 3 o'clock in the morning. You get on a baseband network 2 or 3 o'clock in the morning, it's probably yours. Everything's so fast. Now broadband, what's broadband? Yeah, you're sharing the bandwidth, right? So you don't get the full bandwidth, you get a little section of that bandwidth. But you're almost guaranteed time. You're almost guaranteed time. And we broadband baseband is pretty good, except every once in a while we'll get a little message here because we don't have most of our servers, main servers, are all on the Birmingham campus. So every once in a while we'll get a little box pop up that says network is busy because we don't have a real high speed line. We don't have fiber going over there, or do we? Say we might now, but we still have problems when we try to access the servers on the other network. So y'all see that every once in a while when I try to load something, it'll come up and say network is busy. Retry later. Of course, how much is later? As soon as I can click on it again, right? So, but we have that problem because it's what? It's a baseband network. If it was broadband, then so most local area networks use baseband. It uses Ethernet. Either it uses hardwired Ethernet or it uses Wi-Fi. Wi-Fi is just Ethernet, but it's over the air. It's still baseband, right? You understand that? Internet is not baseband. I mean, internet is broadband, what we call frequency domain multiplexer. So digital, we deal with time domain multiplexers because it takes a lot to modulate. So what they do is they have to have a modem. What's a modem? So when we place information on a carrier, we call that modulation. When we take the information off the carrier and strip it off the carrier, we call that demodulation. So what's a modem? It's a modulator demodulator, right? And that's what it's doing. So it's taking your information and placing it on a carrier at a higher frequency, and then when it gets where it needs to go, it has to go through the demodulator to strip the carrier off, which is basically the way radio works. So you're out there on your car, what do you tune in? You tune in a carrier. So that's what you're doing on that dial. You're tuning in a carrier. And what do you do to the other carriers? Well, you just ignore them because your radio is not tuned to them, right? So these multiplexers that we're using in digital, these are time domain multiplexers. I think we're using a 74. What multiplexer are we using? 151. Okay. So let's find a 74 LS157. Oh, I'm sorry, 154. I got another one on my mind. 151. I'm sorry. For some reason, I had a 157 on my head. Okay, so I got one, and it's a 16-pin deal, and the pins have been done on that one. Okay, guys, what's the power pins? Pretty straightforward. So if you got a TTL chip, you know, that's a good place to start if you don't have the pin out. Okay, what else do we need? Why do I have an extra one up here? Joey's not here. So what does it say we need to do? For all the circuits, use the trainer switches. Okay, so we're going to use the trainer switches, and we're going to use the LEDs for the output, right? Open some of the data switches. So we're going to use the select. So I need selects, right? So what do we use? We'll just use 0, 1, 0, 1, and 2. So what's the select pins? Y'all did Yeah, for the 74,151. Okay, so 9. Are we okay? Everybody agree with that? Are we okay? Everybody agree with that? Okay. What's wrong, Barry? You okay? No, book don't have all the pinouts, by the way, so that's why we use the data sheets. So you got it, Barry, on Blackboard? Okay, so what else do we need to hook up? So what does it say? It says construct the circuit. Note that the enable input must be low. Okay, so we got an enable input. What's the enable input? Could be labeled G, could be labeled E, could be labeled S. Huh? And we're going to connect that low, so that's going to leave it enabled all the time, right? Yeah, E on our schematic, but I don't know exactly what it's labeled on. Is it labeled E on the pinout? Strobe, right? So I told y'all these enable pins can be called different things, right? Strobe, they can be called gate, they can be called chip selects, they can be called enable. So the schematic calls it E, but the data sheet we're looking at calls it strobe. And that's pin, what did we say? Pin 7. Okay, and then the ground is hooked up. We got that. Okay, so what does it say we need to do with the outputs? So we got outputs. We got 0, 1, 2, 3, 4, 5, 6, 7. We got, I'm sorry, these are inputs. We got 0, 1, 2, 3, 4, 5, 6, 7. And then we got outputs, which, okay, what's the difference between the Y and what's the difference between the W? Isn't it Y and W? Got two outputs, right?
Yeah, well,
We can't say it's low, we say it's low active, right? Because if it was low, I would hook it up to a piece of wire. I mean, I'd hook it up to ground. So that means when I put a 1 in, the other one would give me a low out, right? So we're using the Y output. What's the Y output? What pin is that? And we'll hook it up to one of our LEDs. So that way we can watch it flash. Okay, guys, what next? Huh? That's my excuse. But my computer hadn't turned off once since I put that other battery in there. Well, I'm still saying a little prayer because sometimes it does that. Sometimes it'll work for quite a while, but it's a good sign. So what do we need to do now, right? In the circuit in Figure 1, open some of the data inputs and address them to outputs. What output logic is indicated with an open input? Okay. So what we're going to do is we're going to look at it, turn it on. And what do we got now? So I'm going to come over here and take our clock, and I'm going to turn it down real slow so we can see it working. So instead of using your function generator, if you need a clock, you can just do what? This is a TTL clock. This is a generator, so that's controlled by this knob up here, where these are AC. Okay, y'all understand that? And then this is the DC offset right here. So you could get digital out of this function generator right here. This is a sine wave, this is a triangle wave, and this is a pulse waveform. If you used a clock output of your trainer, this is TTL compatible right here. And then this is where we set our frequency right here. Now this is not perfect. You can check it with a scope. So this is your rough, this is your coarse. So if I put it on 1 hertz, that should be fine. And then this is where you'd fine adjust it right here. That makes sense? And most of the time these frequencies are not critical. All you're doing is looking at, if you put a clock in, you might be expecting a watt, either a clock out or whatever. So this is a lot easier to use than trying to use that function generator. Now the triangle wave, we had to use the function generator, right? You understand that? So I'm going to take this and hook it up to one of our inputs. Where's input 0? Huh? It looks like we got something wrong. What's the Y output? I'm going to use these switches up here because I know my two switch on this trainer's got problems. So right now I've got 7, 6, and 5. They're all low. So what output am I selecting? So I got ground hooked up to pin 8. I got power hooked up to pin. There we go. Okay. All right, can you see what it's doing? So I've got 0 input selected. Now what I'm going to do, I'm going to move to another input. So this is floating input. So what does this gate see a floating input as? A high, and most TTL gates do that, right? Not all of them, but this guy does. Yeah. So we can't say always. Your basic gates will always I'll use always there. Your basic TTL gates will always assume or take an open input as a high. Huh? Yeah. Yeah. And so AND gates, OR gates, these are all floating input. It will assume a high. When you get into these gates right here, it's not. So here comes. I got 0 selected. So what's input 0? Okay, so I got it on 4. What's input 1? So why ain't it flashing? Because I'm selecting input. I'm sending input 0 to the output. Y'all understand that? So my select input is selecting which input goes through to the output. Right now I have all these low, so that's a 0. So I'm selecting input 0. Well, where do I have my clock at? Well, I got my clock on input 1. How do I pass input 1 through? Well, I'll come over here and select a 1. I thought I would. So what's input 1? I got my switches backwards. So I got it on 3. Okay, so this is input 1. And now I'm passing input 1 through, right? Y'all understand? Yes or no? Yes or no? So, go ahead. I'm running output Y up in it. So what we got, we've got this situation right here. So if you could think of a multiplexer as being a switch, And what I've got is I've got all these inputs. How many inputs do I have? I'm not going to draw all 8 of them, but let's say we have a 3-input multiplexer. I bring these in, so this would be N0. This right here might be N1. This might be here N2. And then what I've got is I've got a switch over here that I've got the Y output. But what I'm doing is I'm changing the position of the switch with my select inputs. So right now, if I've got it in this position there, what comes through? Well, input 0 would come through to the Y output. If I switch it down here, input 0 is not going to come through anymore because I've selected what input? I've selected input 1. Understand that? So we're electronically switching those switches with those select inputs, S0, S1, and S2. Right now, and we've got inputs labeled what? No, it's not off. It's I went out of my PowerPoints. So Alt D doesn't work. No. Trying to go to the desktop. It didn't do anything. So what we have here is here's my select inputs. They're coming down from my switches. So right now, here's my function generator coming in right here, my clock input, and I've got it hooked up to pin 3. What input is pin 3? Okay, input what? Input 1, right? Yeah. So I've got a 1 selected up here. I'm going to take this and go back to input 0 and it stops flashing. Why does it stop flashing? Well, I'm selecting input 1. I'm sorry, I'm selecting input 0. What do I have hooked up to input 0? We can hook something, let's hook something up to it. Okay, so I'm going to come up here, input 0 is what pin? 4? Okay, I'm going to come up here and bring it up to this switch right here. And I'm going to come over and start flipping this switch. Okay, now I'm going to move over to input 1. Now the switch doesn't make any difference. I can sit here all day and flip the switch. It's not going to do anything because I'm not selecting input 0 anymore, right? I'm selecting input 1. And that's where I got my clock. Here's input 3. Okay, now it goes high because I don't have anything hooked up to it, right? You understand that? What's input 3? It's pin what? Pin 1? Okay, so I'm going to move it over to pin 1, and now it starts flashing, right? Because now I've selected input 3, and I've got my clock on input 3. Here's input 4. It goes high. Why does it go high? I'm selecting input 4, but there's nothing hooked up to input 4. So let's say I'm going to route that input over there. So what's input 4? What pin is input 4? Okay, so there's pin 15, and now it starts flashing. So what we could have is I could have 8 inputs over here, and I can select which input is passed through to the output by the select input. So basically we're doing what? We're electronically moving that switch. So I'm letting 8 inputs share 1 output, but not at the same time. So what is this? Is this broadband, or is this frequency domain, or is it time domain? It's time domain because I'm switching one at a time. Now, what do we make? Well, what do we multiplex for? Well, we multiplex to save wires, or to save media is probably a bigger term. Sometimes we do it to save money. So why do they multiplex Ethernet? Yeah, it's a lot cheaper, right? And it works really good. Well, I mean, especially if you're running a new one. The problem is here, with the switches and everything we have over here is still 100 megabit. Even though we have gigabit Ethernet, If you go to a higher standard, then you got to change all the equipment in the whole network. So we do have some gigabit Ethernet around here, but it's not in this building. It's not in this room. It's actually in this building, but it's not in this room. So they'd have to come up to that big old box up there. They would have to put us a whole new switch up there. So the access point hooks in, the wireless access point hooks up to that thing in the top, and then all those other hooks up to there. So see that thing up at the top up there, it's got all those wires on it. That's what we call a switch. If I went to a gigabit, what would they have to do? They'd have to gigabit. Yeah, exactly right. They'd have to get a gigabit switch, and that would be a lot of money for the college. So we're running on a 100 megabit network down here. So how far do we want to go? So I'm on input 4. So let's select input 5. It goes high again. So I'm gonna move over to input 5. What pin would that be? Okay, so there it is. See that? Ain't that neat? And then this is a 6. So what's input 6? And there it is flashing again. Here's a 7. Where's input 7? So there's input 12. Of course, I'm only using one input, but you can imagine these inputs could be anything, right? And then we select which one goes to the output by the select inputs. And this is a multiplexer. Sometimes we have no option. We've only got one air, right? So when they multiplex through the air, they got no option. You know, you either do it through the air or you do it through cable. And this is what I was talking about. Wouldn't it be awful if you had one channel, if you had one cable for every channel? That would be unmultiplexed. And what you'd be doing on your tuner, you would be selecting a different cable, right? So no. Of course, what does the cable use? Does it use baseband or broadband? Yeah, broadband. You can look up those channel numbers. Every channel is assigned a bandwidth. They're assigned a certain bandwidth. I don't know what broadcast TV is. They changed it around a little bit when they went to high definition TV. But yeah, it's a bandwidth. Every channel is assigned to a bandwidth. You can look those up. You can look up carrier frequencies for every channel on your TV. They're listed. Huh? Did I say broadband? No, I don't know what the bandwidth is. I don't know what the bandwidth for the channels are now. But you can find that. Every channel's got a certain bandwidth, and they have to stay within that bandwidth. If they bleed out of those bandwidths, who comes and gets them? FCC. Yeah. Go ahead.
Is that why, like, people in Tuscaloosa can't pick up channels up here in Birmingham?
Well, no. Now most of your channels go through cable companies. And then the cable companies decide what frequency, what carrier they use for different channels. So that means when I was on the Bright House, my channels were different than my sister's that was on Charter. But that all deals with the cable company and what they modulate them at and what channels they put on there. But every channel number is assigned a bandwidth. And it's up to the cable company what information to put on that carrier, right? You understand? So that's why channels would be different. They're probably pretty standard now because just about the whole state of Alabama is over on Charter now, I believe, or Spectrum now. So they bought Bright House out, and some of your channels moved around. Some of them didn't, but so. What else do we do in this lab? We got time to do another one? Maybe. That's the next one is a 74154. So that's the one I had in my mind. No, I had a 74157, but 74154. So do y'all have any questions about this? So what do y'all need to do here? So back here on page So on page 101, what do you need to do? Write the pin out, right? On page 114, you need to do the pin out there too, right? Y'all understand that? I mean, I'm sorry, 102. Lab 14. Now it says, but step 4, so step 3 says do what? Open some of the inputs and see what there's. So what's an open input on a 74-151? What's it taken as? It's taken as a high, right? Then what does it say for us to do in step 3? Let's make sure we did that. We did step 1, we built the circuit. We built step 2, we built the circuit. Step 3, we opened some of the pins, right? It says open some of the data pins and open some of the address pins. So right now I have input 7 selected. So let's flip it back. Now I'm selecting input 0. It went high, so I need to move my clock over to input 0. What pin was that? Okay, it starts flashing again. So what I'm going to do is I'm going to pull one of the wires out of my select pin. And it went high, right? You understand? So let's see where it went to. So I pulled it out of my C input, so that means I'm selecting a 4, so it's input 4. Okay, it starts flashing. So an open select pin, so on this chip, all your inputs, if you leave them floating, they're accepted as a what? A high. Y'all understand what the term floating means? It means it's open, right? Any more? So that would answer number 3. What does number 4 want us to do? Now open 1 or 2 address pins and check the output logic again. What effect does an open one of the 3 address pins? So that's your select pins. Are you okay? The 74154 is a dual purpose chip. It can be used as a decoder, or it can be used as a demultiplexer. If used as a decoder, the enable inputs are tied low, and the 4-bit binary inputs A0 through A7 or select 0, I'm going to say A0 through A3 or select ABC, right? You understand that? When demultiplexing, the A inputs are used as the address data selector. So it wants us to construct this circuit with a 74-154. I don't know if we need to use a 74-154. Y'all know what a 74-154 looks like? It's a 16-pin decoder. Not 60. It's a 4 to 16 decoder. So the standard size of the dip stayed about the same width for up to a 24-pin dip. When we got to the 74-154, I think I passed this out to y'all, right? They had to go to a 24-pin dip. So look what they did on a 24-pin dip. They just about doubled the width of the IC. And this was around for all your microprocessors spacing. So originally your microprocessors, your 8088, 6800, your 6808, your 8080s, and then when they came out with the 74138, they changed over to what we call a pin grid array. So the biggest one of these guys I ever seen was a 68,000 Motorola processor, and it was a 64-pin dip. So that sucker was about this big. We used to have one around here somewhere. We didn't have the processor, but we had it on the motherboard. I wish I could find that, because that was a big chip. Then after that, they decided to start coming out from the sides and then the bottoms, right? So most of your microprocessors now come out, the pins come out the bottom. Huh? They use this spacing right here. The biggest one I ever saw was the Motorola, and it was a 68,000 processor, and that was the biggest one that I saw use this station right here. I'm not saying they're not anymore. And it was a 64. That's the biggest one I ever saw, and it was a 64 pin deal, 32 pins up each side. Most of the original microprocessors, the 8088, the Z80, the 8088, the 6800, these were in 40 pin dips. Now we have some of the 40 pin dips around here. We got some of those. The Z80 is still around. It's used a lot in a control application. It's a really neat chip too. The 8085 is a microcomputer chip. It's still used widely in a lot. But originally we had three big chip integrated microprocessor manufacturers. We had Intel, which is still making them, right? And then we had Motorola. And then we had a company called Zilog. Zilog basically was a bunch of engineers left Intel and decided to start their own company. And they took the 8088 processor and put two of everything in it. It's a really cool processor called the Z80. Texas Instrument, we had a bunch of companies that got into it after a while. We had Cyrus got into it, but they were making compatible processors. Intel made a processor, but I can't remember exactly what they called it. In fact, I think not Intel, Texas Instrument. They make processors, but their processors never cut on like Intel's. Now we got two big processor manufacturers. We got that make desktops. Who makes desktop microprocessors? Intel and AMD. And then iPhone processors are usually proprietary. They're made by the companies that make the iPhone. Well, I doubt if Apple makes them, but they have them made for them. Apple probably don't even assemble their phones. I think most of those are assembled. Okay, the 74154. Okay, what's the power pin on 74154? So this is pretty neat too. This is okay, and what's the ground pin? Okay, so what we're going to do with the 74154. So let's look at the pinout and we'll see about what we need to do with this. Oh, I don't have Internet Explorer open anymore. So do we have the pin out of the 74154? So what we're going to do is we're going to basically try to enable this thing all the time. And this guy's got 3 enable inputs on it, right? Don't it have 3? If I remember right. Oops, let me. So we have a, huh? Thank you. I think say that's not it. So this is a decoder demultiplexer, right? Probably a 138 would work better than a 154 than what we're using here. Because here we could actually decode 16 outputs, but we're only going to use 8 of them. Our enable pins, it's got 2 of them. I thought it had more. It's got the G1 and the G2. So to get this thing to decode, we need to bring the G1 and the G2 low. What we're going to do is just bring one of them low. Let's bring the G2 low. What's that pin? Huh? So this is 12, 13, 14, 15, 16, 17, 18, 19. Okay. All right. Now I'm going to take my Y output, which is what pin? The Y output on my encoder, and I'm going to hook this up to the G2, the G1 input, which is pin 18, right? Huh? I'm back on my multiplexer. So we're taking the Y output of our multiplexer, and we're going to bring it into the G1 input. So the Y output is 1, 2, 3, 4, 5. That's the one that's still hooked up to the LED. Okay. Now what are we going to do? Well, we're going to take some wire, and we're going to hook them up to our LEDs. So what's the 0 output of my? No, I'm sorry. We need to bring the select inputs over. So from my encoder, I'm going to take, from my multiplexer, I'm going to take the 0 input or the A input, and I'm going to hook it up to the A input of the 74154. What's the A input of the 74154? A input. 23. I'm going to take the B input that's coming from that's connected to my 74151, and I'm going to hook it to the B input of my 74154. What's the B input of that? Just comes right down the line, right? And then I'm going to take the C input of my multiplexer and hook it to the C input here. I'm going to take the D input and I'm going to connect it low. Because we only have an ABCD output coming out of our multiplexer and we have an ABCD input coming on our decoder, so we don't want to select D all the time. So we're almost there, guys. We'll finish this lab up at the start of class, and then we'll look at something else. So. In fact, I'll probably go ahead and finish wiring it up tonight, and then that way you will come right in and we'll be able to finish this lab up. No. What question do you want to ask me? This would have worked a lot better with the 74138 because the 74138 is a 3 to 8, right? So I don't know why they decided to use the 74154. Yeah, this looks good. Huh?
So you know the data inputs and that's fine like that.
Yeah, I mean, that's fine. You okay? Yeah, it is. It's a 138, So we're using a 154 to do an octal, the binary. So that's why we're wasting the D pin. We could do this. We could demultiplex it with a 138, which would be yeah. But we're demultiplexing it with a binary to hex. So we're wasting a bunch of pins. So the only outputs we're going to use is 0 through 7, and this guy here's got 0 through 15. So we could do this lab with a 138 instead of a 154. I mean, instead of a 7454. Good, go ahead.
Sure. We got our outputs.
Yeah, normally we put the pin numbers on. Okay, you'll just run out of room, but we've got these things hooked up too, right?
Inverters.
We need to pin out on those.
On inverters. So once inverters come in here, the inputs for the 74 LS 147.
That's right.
And they come down here and put the outputs.
The outputs would be the ABCD outputs. Don't worry about connecting up this guy down here because it's.
So I'm on the right track.
Yes, you're on exactly the right track. Oh, they don't have anything hooked up to the input, and I got it turned all the way down. So this is one way you can check to see if your probe's working. Let's see, that's the wrong one. Is this scope has so much input impedance.
Oh man, okay.
Where's this coming from? What frequency is it? 60 cycles. So this thing, I'm picking up 60 cycles all the time. So I got my scope turned down. I got it on. Normally, to check and see if a scope probe's working, you just you put it on and just touch it with your finger. You want to touch it? What's that? So this is basically what touchscreens and everything's using. So that's why we have two types of touchscreens. We have a resistive touchscreen, which you can touch with anything. And then we have what we call a capacitive touchscreen, which is what these uses. So that's what it's doing. It's picking up. Oh, y'all can't see that. It's picking up that. Yeah, it's picking up with a capacitive. So that's why you can't just touch this with anything. You either got to use your finger or you got to use a special stylus. The touchscreen on the HMI panel over on the Amtro line it's a resistive. So what it does is when you press on it, it changes the resistance. So you can touch that thing with anything. So capacitive is only. So that's why if you do it with your fingernail, it won't pick you up, right? Because your fingernail's a real good insulator. So that's all it is. These are capacitive displays. That's what they are. What's that? I told her I had her keys. Undoubtedly, she don't need them. Where they at? I know. I put them. They're up here. They're up here somewhere. She'll probably run by here in the morning. She don't have to go over to Birmingham. These are just for keys to A building, so she don't. Yeah. Okay. I put your name in there. It corrected it over to Hobart. All right. Sometimes autocorrect is the pitch. it.